Hi, I'm John, and I'm excited to present our paper, Latent Agents, a post-training procedure for internalized multi-agent debate. Multi-agent communication methods, most famously multi-agent debate, can improve reasoning and factuality. However, these methods are slow and expensive since they require running multiple models over many conversational turns. This led us to raise two questions. One, can we distill multi-agent reasoning into a single language model? And two, if we can we identify and control the internalized agents? To answer the first question, we introduced IMAD, a two-stage fine-tuning method that distills multi-agent reasoning into a single LLM. We first start by collecting a debate dataset. We use a three-agent, two-round debate setting and use simple arithmetic expressions as our problems. This is intended to focus on the model structure learning rather than reasoning of the problems itself, and use simple arithmetic expressions as problems. This is intended to focus the model on structure learning rather than reasoning of the problems itself. Debate tags that highlight different stages of debate, such as rounds and agent responses, are added to assist debate structure learning and to provide target rewards in the training stage. Using the collected debate dataset, we first perform debate structure learning. The goal of this stage is to teach the base LLM to mimic the conversational structure and format of debate. This includes components like multiple agent responses, iterative refinement over rounds, and final consensus. To achieve this, we perform supervised fine-tuning on the full debate transcripts. The resulting model outputs full debate traces as if it is simulating multi-agent debate. Next, we employ a second optimization stage for debate internalization. Through this stage, instead of performing debate externally via text, we want to teach the model to conduct it internally. For debate internalization, we fine-tune the model from the previous stage using GRPO with dynamic rewards. We have two key components in the reward function. First, the formatting reward incentivizes the model if its output contains the debate tags from the dataset. Also, as training progresses, the weight for this reward is decayed towards 0. This is to reward initial adherence to explicit debates and then gradually reduce the incentive for verbose generation as the model learns to internalize. The second component is the correctness with length clipping reward. Inspired by recent work that achieves latent reasoning by progressively shortening the model outputs, we truncate the model output to a length limit, L, then only give rewards when the correct answer is contained within this truncated output. Throughout the training process, this limit L is gradually decreased until we arrive at the target length L star. This creates a gradual pressure on the model to place the answer within the length limit. These two rewards work together to make the model to perform debate reasoning learned during the SFT stage internally instead of verbalizing. Here we present qualitative results of IMAD against different baselines. Across different base models and benchmarks, IMAD matches or exceeds the performance of explicit debates. More importantly, IMAD consumes far less tokens, using only 6 to 21% of the tokens compared to debates. IMAD can reap the benefits of multi-agent debates while having the efficiency of a single model. Now that we know that our method works, we want to answer the second question: can we identify and control internalized agents? For this, we extract and use agent-specific steering vectors. For each target agent I, we construct contrastive activation pairs by providing the model with identical context, which is the problem and the debate history up to the target agent's responses. For positive activation, we append the target agent's response to the context. For negative activation, we append the response from the other agents. The steering vector for agent I is the difference in means of the activation pairs from the SFT-only model. Using this technique, we first need to answer the question, Do internalized agents persist as identifiable structures? To investigate, we first internalize debate with agents that have distinct reasoning styles. Then, we steer the IMAD model using agent-specific steering vectors, and observe output faithfulness of the steered models with the original agent responses. The figure here shows Rouge L scores of steered Bayes and IMAD models, averaged across 3 agents. Steered IMAD shows a higher area under the curve and consistently higher Rouge scores across all steering coefficients, indicating stronger alignment with target agent behaviors. This suggests that agent subspaces created by IMAD are identifiable and separable. Now that we know that internalization creates identifiable agent subspaces, we now want to know whether IMAD enables post-hoc control of undesirable agent behaviors. Here we demonstrate a potential application in LLM safety. For the experiment, we inject a malicious agent in debates and internalize it via IMAD. We test 2 malicious traits, evil and hallucination. Then we apply negative steering using the steering vectors of the malicious agents, and then see if we can localize and suppress harmful behavior without collateral damage to the general task performance. Here are the results measuring trait scores, perplexity, and GSMAK accuracy of steered Bayes and IMAD models. For the evil trait, IMAD achieves earlier complete suppression of malicious behavior, while the Bayes model still retains some behavior at max negative coefficients. IMAD also maintains stable GSM task performance across the full steering range, indicating that steering does not affect general performance. Finally, IMAD maintains or improves perplexity across all conditions, suggesting that steering does not degrade output quality. We have similar results for the hallucination trait, except that both Bayes and IMAD models achieve partial and not complete suppression. Overall, the results indicate that IMAD creates separable behavioral representations that can be suppressed or amplified without disrupting the model's core capabilities. To summarize some takeaways from our work, IMAD achieves performance of multi-agent debate at a fraction of the token cost. Internalization preserves separable agent subspaces, and internalized agents are safer and easier to steer. Thank you for listening to our talk.